Okay. May, June 2020, paper 4, variant 1. Question 1. An airplane of mass 2.5 times 10 to the power of 5 kilograms lands at the speed of with a speed of 62 meters per second. Okay, on a horizontal runway at time t equals 0. The airplane decelerates uniformly as it travels until it reaches a speed of 6 meters per second at t 35 seconds. Can I calculate the deceleration? Yes, definitely I can calculate the deceleration, which is basically v minus u over t. V minus u over t, which is 62 minus 6 over 35. 62 minus 6 over 35, which is exactly 1.6 meters per second squared. Yes, 1.6 meters per second squared. The resultant force, can I find the resultant force? Yes, force equals ma. Force equals ma. Do I have the mass? 2.5 times 10 to the power of 5 times the acceleration, which is 1.6. Acceleration 1.6. So the resultant force would be around 4 times 10 to the power of 5 newtons. The momentum of the airplane when its speed is 6 meters per second, momentum equals mv. P equals mv. We have the mass 2.5 times 10 to the power of 5 and the velocity, which is 6, which gives a momentum of 1.5 times 10 to the power of 6. 1.5 times 10 to the power of 6 kilograms dot meters per second. Okay. Yeah. At time 35 seconds, the airplane stops decelerating and moves along the runway at a constant speed. At a constant speed for a further 15 seconds, up to 50. From times t0 to time 35, what was happening from time t0 to time 35? What was happening to the speed? The speed was decreasing. And on this graph, we have a distance time graph. How can we draw a distance time graph? Okay, how can we draw a decreasing speed on a distance time graph? It should be curving towards the time axis. Slope should be decreasing. Slope should be decreasing. And then from 35 to 50, the speed was constant. The speed was constant, which is a straight line moving upwards from 35 to 50. This should be a straight line moving upwards. Okay, it could reach any point at 50 seconds. At 50 seconds. Huh. As the airplane decelerates, the kinetic energy decreases. What happens to this kinetic energy? Due to the brakes, this kinetic energy is transferred as transferred as what? Transferred, yes, as thermal energy, or heat energy, or whatever, lost to the environment as heat energy. Question 2, we have an extension load graph. State the ranges for which S obeys Hooke's law. Okay, spring S obeys Hooke's law. Okay, a range of loads starting from 0 to 4, 6, 8. Yes, up till 8 newtons. From 0 newtons to 8 newtons. Using the information, can I find the spring constant? Yes, I can find the spring's constant, which would be F equals kx, so k equals F over x. F equals kx, so k equals F over x. The force would be 8 newtons and the extension would be 15. So 8 over 15, which is around 0.53. 0.53 newtons per centimeter. 0.5333, I know. 0.53 newtons per centimeter. Ah, that's easy. A second spring identical to the spring S, second spring identical to spring S, was attached to it, and a load of 4 newtons was suspended from the bottom, and they are in equilibrium. State the name of the form of energy in the springs as they are stretched. Definitely, the form of energy would be elastic potential energy or strain potential energy. Okay, elastic potential energy. Okay, determine the extension for the arrangement. The extension for the arrangement, if we have two springs in series, what happens to the total extension? Total extension is multiplied by 2. What do I mean by that? Can I find the extension for the spring at 4 newtons? For one spring, can I find the extension for spring S at 4 newtons? Yes. How can I do it? I can use the equation F1 over x1 equals F2 over x2. F1 over x1 equals F2 over x2, in which the original force which we used from the previous question was 8 over 15. When the force was 8 newtons, the extension was 15. Therefore, if you add a force of 4 newtons, can I find the extension? Yes, cross multiplication. So basically 4 times 15 over 8 would be 7.5 centimeters. But this is for only spring S. This is for spring S. What about the other spring? It would have the same extension since it's an identical spring. So both of them would have extensions of 7.5 centimeters. We can add them up. Okay, we can add them up to have a total extension of 15 centimeters, or basically you can just say 7.5 times 2. 7.5 times 2, 15 centimeters. Moving on to the next question. The load is carefully increased to 6 newtons in total. The load is now 6 newtons. Can I find the distance moved? Can you find the distance moved to the new equilibrium as it increases from 4 newtons to 6 newtons? Yes, we can do that. As it moves from 4 newtons to um, 6 newtons. Well, can you find extension at 6 newtons? Yes, we can find extension at 6 newtons. Again, we can use the same equation. So 8 over 15 equals 6 over x2. 6 over x2. If you cross multiply, this would give you an answer, a final answer, or x2 would be 11.25. Okay, this would be 11.25. If we multiply it by 2, because we have two springs, this would be 22.5. 22.5. This is the new extension. This is the new extension. Can I find how long it moved? Okay, what is the distance it moved from this extension to this new extension? Yes, all you do is 22.5 minus 7.5, minus 15, which is 7.5. 22.5 minus 15, which is a distance of 7.5 centimeters. Okay? Okay. Now, moving on to the next question. This is a manometer. It has been removed. Okay, this question has been removed, so we don't need to answer question A. Question B, we can answer question B. This is the only part of this question that we can actually solve. Why? Because the remainder of the question has been removed from the syllabus. Explain in terms of momentum, okay, of its molecules why the trapped gas exerts a pressure on the walls of the tube. We know that gas molecules move fast and random. They move fast and random, colliding with the walls. As they collide with the walls, what happens? They change their momentum, changing their momentum. As they change their momentum, what happens? Causing a force, causing a force over an area, over an area, which is pressure. Okay, so this is the only part of this question in which you are required to solve. Okay, uh, part C again is cancelled. Okay, this whole question is cancelled, so we can move on. Question 4, what is a boiling point? What's the boiling point? It's a temperature at which the liquid can change to gas. It's a temperature, okay, a temperature at which liquid turns to gas. Okay. Um, Calculate the energy transferred from the water. Can I calculate the energy transferred from the water? E equals mc delta T. E equals mc delta T. We have the specific heat capacity, you have the mass of the water, and you have the delta T. Okay, from the water. Okay, this is the question. I know probably some of you have solved this question wrong. From the water is now at a boiling point, at its boiling point, which is what? Which is 100 degrees Celsius. After a few seconds, the temperature of the container and the water are both 95 seconds. So initially it was 100 degrees Celsius and finally the temperature became 95 degrees Celsius. So the loss in temperature, the delta T, the change in temperature would be 5 degrees Celsius. So E equals mc delta T, in which the mass is zero point 0.3, C is 4,200, and the delta T, which is 100 minus 8, minus 95. This would give you an energy of 6,000, around 6,300 joules. صح. Uh, part II is cancelled. Thermal capacity has been removed from the syllabus, so you're not required to solve this part. Water from the container evaporates and the temperature of the remaining water decreases slowly. Explain in terms of molecules why evaporation causes the temperature of the remaining water to decrease. We know evaporation. What happens during evaporation? The most energetic molecules escape. The most energetic molecules escape from where? From the surface. Escape from the surface, leaving behind the least energetic molecules. Leaving behind the least energetic molecules, causing decrease or decreasing the average temperature, decreasing the average temperature. What is meant by the principal focus for a thin converging lens? Principal focus. It's a point at which, okay, point at which, it's actually a point on the principal axis. A point on the, it's a point on the principal axis at which all of the parallel rays, all of the parallel rays. هي الفكرة ان هو دلوقتي we have parallel rays, not any rays, all of the parallel rays. Okay, converge and meet. Okay, and meet after passing, converge through and meet after passing through the lens, after passing through the lens. It's a point on the principal axis at which the all of the parallel rays converge and meet after passing through the lens. The lens is used as a magnifying glass. Magnifying glasses have three properties, which are underlined now. Enlarged, real. Are they real? No, they're not real. They are upright and they are virtual. Okay, they are not real. They are virtual. Why are they virtual? Because they do not meet on the the image cannot be produced on a screen. Okay, the image cannot be produced on on a screen. Yeah, this is a rather, I don't want to say difficult question, difficult drawing, but it's a newer, okay, way of solving this question. In this question, we have an image. Okay, we have an image. And he said that this image is a magnifying glass. It's an image produced by a magnifying glass. Images that are produced by magnifying glasses are usually upright, as we said, virtual, enlarged, and on the same side as the object. So they're on the same side as the object. Meaning that if this is the image, then the object would be somewhere at this point, for example. Okay, if this is the image, then the object would be somewhere at this point. First of all, can I draw or mark both principal focuses? Yes, I can mark both principal focuses. The principal focus or the focal length is 5 centimeters. The focal length is what is 5 centimeters. He said that five small squares are 1 centimeter. Five small squares are 1 centimeter. So we can count. Okay, so we have 10, 10, and 5. So this is okay, if I'm not wrong. Um, 1, 2, 3, 4, 5. Yes, so this is 1, 2, 3, 4, 5. Yes, this is F, and then F on the other side would be on this at this point. So we have both principal focuses. So have both focal points. How can I draw the object? How can you draw the object? Since this is a magnifying glass, it's a magnifying glass. The object has to be the distance between the object and the lens has to be less than the focal length. The distance between the object and the lens has to be less than the focal length. So basically, the object should be somewhere at this point. Okay, and it's smaller than the image. Why? Because the image is enlarged. The image has to be enlarged. How can I find the exact point of this? How can you find the exact point of this object? First of all, we need to draw some lines. We need to draw some lines. The easiest line, the easiest ray to draw is the ray from the tip of the image, okay, which again passes through the tip of the object and moves through the center of the lens. So from the tip of the image to the center of the lens, let me draw it again. Again, you're using your rulers. So it's passing through the center of the lens and moving in a straight line. Okay, so this is the first and easiest line. The second line or the second ray is a bit more tricky, and let me explain it while drawing it. The second ray from this image will move through let me use a different color. Which color? Let's use the green one. Okay. The second ray will move from the tip of the image to the focal point, to the other focal point, not this focal point. It actually can do it through this focal point, but through the other focal point first. Okay, through the other focal point first. Somewhat like this. Okay, definitely you're using your ruler. You're using your ruler. It's moving through the other focal point. Okay, somewhat like this. And then at this point, the point at which this line or this ray meets the center or the center of the lens, you will draw another parallel line. You'll draw another parallel line until it reaches this blue line. At this intersection, you have the object. At this intersection, you have your object. So the object would be at this point facing upwards, okay? Object would be at this point facing upwards. How did I draw this green line? how do I know that I have drawn this green line correctly? If you think about it, you have this object O, you have this object O. If you have any object, how do we draw the rays from this object? We draw two main rays. The first ray, which passes through the center, the blue line. Okay, so let's trace it from the object. Let's trace the image from the object. First of all, we draw a straight line from the tip of the object passing through the center. Okay, and then since this is a magnifying glass, it's a virtual image, so you need to extend the rays behind the object. Then the second line, which is the green line, we said you need to draw a line parallel to the object, parallel to the principal focus, okay, from the tip of the object, parallel to the principal axes. And then as it reaches the center of the lens, it gets refracted and passes through the focal point, passes through the principal focus. As it passes through the principal focus, again, you will extend the line back to the image. You'll extend the line back to the image. And that's why I kind of reverse operated this question. Okay. We don't have many questions. I don't think I've seen that many questions regarding if you have an image and not just any image, not just any image, a virtual image, and you're required to find the position of the object. Okay, it's one of the more difficult questions when you have to draw lenses and so on. Okay, so this is how you should find the position of this object. Okay, how you should draw. Definitely, you're using a ruler, so your drawing might be a bit more accurate than mine. I'm just using my freehand, but you should use your ruler to find the exact position of this object. Because he's saying find the distance from the object to the center of the lens. If I find the distance from the object to the center of the lens, my question, or using my drawing, it would be around 1 to 3.8. Okay, 3.8 is not within the range. The range is around 3 centimeters. So actually, my object should be somewhere at this point. Okay, your object should be somewhere at this point. So if you've drawn it quite accurately, the object would be somewhere at this point with a distance of around 3 centimeters, 2.9 centimeters. Okay, you have a range, a small range. Okay, 3 centimeters. Okay, I know this question might be a bit difficult, but again, that's what we're doing now. We need to solve the more difficult questions so that we can get prepared for our final test. The speed of sound in air is 340 meters per second. Calculate the wavelengths. Okay. Calculate the wavelengths or the range of wavelengths for that are audible by a healthy human ear. Again, he said the wavelengths, not the frequencies. As normal humans, or if you have a healthy human ear, you'd be able to listen to frequencies from 20 hertz all the way to 20,000 hertz. From 20 hertz all the way to 20,000 hertz. Can I find the wavelength? Yes, you can find the wavelength. Speed equals wavelength times frequency. So wavelength equals speed over frequency. Speed over frequency. So the speed is 340 meters per second divided by the largest frequency, which is 20,000. This would give you a distance of a wavelength of 0.017. 0.017. And then 340 divided by the smallest frequency, hmm, which is a wavelength of 17 meters. Okay, you have to include the unit. You have to include the unit. Sound waves are longitudinal waves. Describe how a longitudinal wave differs from a transverse wave. A longitudinal wave vibrates, okay, parallel, okay, left and right, parallel to the energy motion, okay, while the transverse waves vibrates up and down perpendicular to the energy motion. Yeah, let's write it down. Longitudinal waves vibrate, vibrate left and right, parallel to the energy motion, while transverse waves vibrate up and down, perpendicular, perpendicular to the energy motion. You can say that the transverse waves also include or also have um, crests and troughs. You can say that the longitudinal waves have rarefactions and compressions. Okay, so the longitudinal waves have compressions and rarefactions. Okay. Okay. Figure 6.1 shows a band in front of a building. The drum produces a low frequency sound. A low frequency sound. Other musical instruments provide high frequency sounds. Okay. These sounds are equally loud, so the amplitude is the same. A young man on the side of the building hears the drum. He can hear the drum, but not the high frequency sounds. Why is this so? Okay, why can he hear the drums but not the other high pitched sounds? When the drum has a low frequency, what happens to the wavelength? The wavelength increases. If you have a low frequency, a lower frequency, the wavelength increases. What happens if you have a higher frequency? What happens to the wavelength? The wavelength decreases. Why is this relevant? Why is this relevant? As the wavelength increases, you have a wall, which could be considered to be a barrier. So this wall is a barrier. The waves will start to diffract. Okay, you have a barrier, and you can say you have a gap. uh, Gap at the end of the barrier. So what happens? What happens? The waves diffract while passing through this barrier. If you increase the wavelength, what happens to the amount of diffraction? The diffraction increases. So all you need to say is that as the frequency decreases, the wavelength increases, so the diffraction increases as well, and that's why it can reach the man. If the diffraction was much less than the diffraction, then the waves wouldn't be able to reach this man. Okay, diffraction increases. Huh. An electromagnet consists of a solenoid X that's made of a copper wire, and the solenoid contains an iron core. Why? The structure of the copper makes it suitable for the iron wire. Why? Because the copper is a good conductor since it has free moving electrons. A good conductor of electricity. Why? Because it has, okay, why? Because it has free moving electrons. Electrons. Why is the iron a suitable material for the core of the electromagnet? Iron is a suitable material for the core of the electromagnet because iron is a temporary magnet. It loses its magnetism easily. It's a temporary magnet. It's a magnetic material. It's a magnetic material, and okay, it's a magnetic material and loses its magnetic field. Instead of saying loses, you can say it's a temporary magnetic material and a temporary magnet. Okay, figure 7.1 shows the electromagnet inside a solenoid Y. So you have solenoid Y. okay, and the uh, temporary magnet or the electromagnet inside it. Describe and explain what happens to solenoid Y when solenoid X is connected to an alternating current power supply. You can actually think of this question. I know it might look a bit difficult from the drawing. Drawing is a bit complicated, but honestly, it's a very, very easy solution. Why? Because you can think of it as a transformer. Okay? You can think of this as a transformer. A transformer has a core, an iron core, and it has two coils. It has two coils, the primary and the secondary coil. So this is almost the same as a transformer. Why? Because you have a coil, which is the iron, you have the iron core, you have solenoid X, which is a coil, you have solenoid Y, which is another coil, and then you have an alternating current. Transformers operate using an alternating current. So what does this alternating current do? The alternating current, the alternating current produces an alternating magnetic field. Alternating magnetic field. طيب, what does this alternating magnetic field do? What does it do? It cuts, okay? Cutting the coil Y, okay? Coil Y, producing hmm, an alternating induced current and EMF. Producing an alternating induced current and EMF. Okay, um, in Y. Okay, in Y. Okay, a switch and a lamp are connected in series with the terminals of solenoid Y. When the switch is closed, the lamps light up. The lamp lights up, okay, at normal brightness. Describe and explain what happens to the current in solenoid X when the switch is closed. Okay, when the switch is closed. The current in X, I guess, will increase. Why will it increase? Because it needs to light up this lamp. It needs to light up the lamp. So the lamp needs to use some of the current. From where will it get this current? From X. So you need to increase the current in X. Okay, the current in X. Okay, needs to. You can say it. The current. In X increases. Why does it increase? To light up the lamp. Okay, to light up the lamp. Yeah. To light up the lamp. Okay, needs to supply some of the power from for this lamp. The power supply used in an electric vehicle contains 990 rechargeable cells, each of an electromotive force of 1.2 volts. 990 rechargeable cells, each of 1.2 volts. The cells are contained in packs which are all in series. Okay, they're in series. The AMF of each pack is 54 volts. Can I find the number of packs? Yes, I can find the number of packs. How can I find the number of packs? First of all, can I find the total EMF? Can you find the total EMF? Yes, we can find the total EMF, which is basically 990 times 1.2. This is the total EMF. 990 times 1.2 is 1188. 1188 volts. This is the total EMF of the whole power supply. What is the voltage of each pack? The voltage of each pack, the potential difference of each pack is what is 54 volts. So 1188 divided by 54 would give you a total of 22 packs. 22 packs. Why? Because each pack has a voltage of 54. 22 times 54 would give you 1188. When in use, each pack supplies a current of 3.5 amperes. Calculate the rate at which each cell is transferring chemical energy to electrical energy. What is the rate of transferring energy? Rate of transferring energy is power. Rate of transferring energy is power. So basically, we need to calculate the power. Power equals IV. So do you have the current? Yes, 3.5. The voltage, I'm not asking about the voltage of each pack. I'm asking about the voltage of cell, each cell, which would be 1.2 volts. So 3.5 times 1.2 is 4.2 watts. 4.2 watts. Yeah. The packs are connected in parallel to supply a large current to drive the electrical vehicle. Explain why is it necessary to use thick wires? Why do we need to use thick wires? As you increase the area, as you increase the cross-sectional area of wires, what happens? The resistance decreases. The resistance decreases. So as thickness increases, resistance, okay, resistance decreases. Why? Because they're inversely proportional. When the thickness or when the resistance decreases, this means that we have less power lost. So less power, less power and less power and energy lost. When you have less power and energy lost, this is more efficient. Okay, this is more efficient. Why is this more efficient? Because you won't have to spend that much money. Okay, you're actually using up most of the you're actually using up most of this energy. You're not wasting most of the energy. Okay, so it's more efficient now. Question 9. We need to solve only part A. Only part A. Part B is cancelled. Okay, part B and C are cancelled. Only part A. Describe how a digital signal differs from an analog signal. You may draw a diagram. A digital signal would have a diagram of 1, 0, 1, 0, 1, 0. Okay, so this is alternating between 0 and 1. This is a digital signal. An analog signal would have values ranging from whatever value to whatever value, but it's a continuous range. It's a continuous range. So basically, a digital signals contains only signals of 1 and 0, high and low, on, off. Okay, digital. Okay, signals. Okay, which are only digital, only 1 and 0, high and low. You can say on and off. That's all you have in digital signals. Okay, on and off. Okay, voltage or whatever. What about the analog signals? Analog. Okay. Um, Analog signals continuously vary between two values. Okay, continuously. You have to say continuously. Okay, vary between two values. Okay, they continuously vary between two values. Okay, whatever two values you have in the, for example, if you can vary between, let's say, 25 and 0, so this is an analog signal. Okay, it's not 1 and 0 only. You have a range. You can go up and go down, if as long as you're within this range. As long as you're within this range. Okay. Yeah. Question B and C, or part B and C, are cancelled. Yeah. Question 10. State one similarity between this atom and a neutral atom of a different isotope of element X. So this is element X. One similarity is that they have the same number of their isotopes, same number of protons. Same number of protons. Hmm. The isotope of element X is radioactive. It decays by emitting a beta particle. Decays by emitting a beta particle. Can I find the Y? Can I find the nuclide notation of Y? Yes, we need to write down the chemical equation. We need to write down the whole equation. What happens? X. What does X consist of? Let's count them. Okay, it consists of 5 protons. 5 protons. And how many neutrons? You have 4 and 4, so 8 neutrons, which is a total of 13. So when we write down X, you have to write down X, which is 13 and 5. 13 and 5. It produces a beta and Y particle. It produces a beta and Y particle. We know that beta is 0 and -1. So Y would be 13 and 6. Okay, Y increases by 1. When you produce a beta particle, the atomic number increases by 1, but the proton atomic number increases by 1, but the mass number stays the same. Okay, mass number stays the same. Beta particles ionize the air as they pass through less strongly than the same number of alpha particles. Why is this so? Why is this so? Beta particles, why do they have a less ionization effect? Basically, because beta particles are, you have so many properties, okay? They're smaller, okay? Yes, they are smaller. What about the charge? You can say that they have less charge. They have less energy. Okay, they have a smaller mass. Okay, you can say that they have a smaller size. Okay, so they have a smaller size and mass. And mass. You can have this have less energy. They have less energy. Okay. You need 3 points. We can talk about the size, the mass, the energy. Okay, the charge itself have less charge. Okay, the distance they travel is much less. The force they have, it's all much less than the alpha particles. Okay.